In the previous video, we took a more deep dive into capacitors and introduced their figure of merit, the capacitance, which was defined to be what you got, the charge held on the plates, over what you had to pay, which was the voltage across the capacitor. Now, we can also recast this to say Q equals C delta V. So we can say that for a given potential being applied across the capacitor, we hold this much charge. So what I want to do here is, for looking at three different geometries of capacitors, I want to see how the shape, or the geometry as physicists often like to say, of the capacitor affects its capacitance. So we'll start with the parallel plate capacitor. And we know that so we'll just assume that the plates are very large compared to the separation. And so we'll treat this like it's effectively infinite. So we'll ignore the fringe field. So with that, we can express the electric field strength between the plates as delta V over D. And we can express the electric field strength in terms of the charge. Now we could just up and remember the formula for it, but I think it might be instructive to just revisit this with Gauss's law. So let's go ahead and, since this is a planar symmetry, we'll erect a Gaussian pizza box like so. Now we remember from our earlier discussion that the charges are going to sit near the at the surface of the conductor, and in the case of this being an infinitely large capacitor, there won't be any charges on the back surface. All the charges will be sitting right on the top of the inner surfaces. So I've erected a Gaussian pizza box that has been chosen so that the top of the box goes right through the conductor. So here on this surface, the electric field is what? Pause the video and get back with me. Yeah, that's right. It's 0 because it's a conductor in equilibrium. So there's no flux through that side. So how about along the edges of the pizza box? Again, the flux will be 0. And this is because although we can have downward facing electric field, our dAs will point out perpendicular. So, So E dotted with dA is 0 because of the right angles. So that only leaves the bottom of the pizza box. So here our areas are going to be pointing downward along with the electric field. So we can go ahead and do Gauss's law for this, say integral E dot dA equals Q in over epsilon naught, where Q is the charge inside. So here we've worked out that the only surface that contributes is this bottom surface. And since the electric field is a constant, you're just going to be saying this is going to be the integral of E times dA. And the charge enclosed is just going to be this charge Q over epsilon naught. And again, you can pull the E out of the integral. And I really hope you can integrate dA all by itself to be left with E times A equals Q over epsilon naught. So where I'm going with this is I'm going to want to get it into this form I was showing you earlier, where I'll have Q on one side, and I eventually want to have a delta V on the other side And then everything in front of the delta V I will identify to be the capacitance. So we remember that the electric field strength we said is delta V over D here because it's a uniform field. A Q over epsilon naught. All right, so then I can rearrange this to get that Q is equal to epsilon naught A over D, times delta V. And if I remember my prototype equation here of Q equals C delta V, like so, then that means I can identify this piece right here to be the capacitance. So we get that for a parallel plate capacitor, the capacitance is epsilon naught A over D. Now, you might ask yourself, well, wait a minute, why did you choose the pizza box to go through the positive plate? What if it were the bottom plate? You could do the bottom plate, and then you would hold a charge of negative Q, but your dA would point up, so the E dot dA would be negative E dA, and the minus signs cancel. So pick your poison. So let's go and think about what this result means for a second. So this is saying that for a given applied voltage, I will hold more charge if the plates are bigger. Okay, that makes sense. If the plates are bigger, since the electric field strength goes as the surface charge density, if I have more plate, then I'm going to need more charge to do that. And it goes inversely as the separation. So what I want in practice are very large plates, very close together, in order to maximize my charge holding capability. Now, like I had mentioned in the previous video, in practice, although parallel plate capacitors do exist for very small capacitances down in the picofarad range, where the devices will typically look like little brown discs once they've been coated with insulating material. What you're more apt to see are cylindrical shapes, and this is because you take long strips of mylar and roll it up like a jelly roll. But it's reasonably analyzed as a cylinder. And also another case where the capacitance really matters in cylindrical form turns out to be with the kind of cable with coaxial cable, which is the kind of cable you use for cable TV and for internet transmission over cable. And in fact, it turns out that it's the capacitance of the wire that dictates your maximum bandwidth. So let's go and take a look at this. So I'm going to imagine that my inner conductor here, I'll assume that this one has a positive charge, plus Q, and I'll say its radius is little a. And then I'm going to have an outer conductor here that's supposed to be concentric around it. There we go. An outer conductor here that's charge minus Q, and radius, let's just call it B. And these are going to be cylindrical shapes, so the inner conductor goes back like this. In practice, there would be insulating material between these, but we'll just assume for now that it's being just held together magically somehow, that the air is keeping them from touching. We'll get into how to deal with the addition of insulating material in a later video. So the positive charges will be uniformly distributed all along the surface of the conductor, the inner conductor here, like so, and the negative charges will all be along the inner surface. And again, I'm going to assume that this is very long, compared to either A or B, so we can approximate this as essentially infinite. And we'll say the length of our capacitor is L. All right, so we could go and, if we remember it, we could look up what the electric field is in a case like this. But again, let's just for practice say we forgot. So what we can do is we can erect a cylindrical Gaussian surface of radius r. And length L, just like the rest of this. And we can go ahead and apply Gauss's law. So to get the electric field strength, this would be integral E dot dA equals Q inside over epsilon naught. So here, my electric field lines are running outward everywhere like this. And anywhere on my Gaussian surface, my dA is also pointing outward. So E and dA are always parallel at every location. So this means that my in my dot product here is just going to evaluate to E times dA. And again, the charge enclosed is just going to be our charge Q. So when doing this, again, remember there will be end caps here on the Gaussian surface and at the end, circular end caps. But there, the dA, say, will point along the axis like so, which will be perpendicular to the electric field. So the flux at the end caps here is 0, again, because the electric field and our dA are perpendicular. So we only have to worry about the long surface part of it. So again, the electric field is going to be constant by the symmetry of the situation, so we can pull that out. We're left with E integral dA is equal to Q over epsilon naught. So we can say EA is equal to Q over epsilon naught. But what is this area? Well, it's 2 pi RL, so we can put that in. E times 2 pi RL equals Q over epsilon naught. All right, so I'm going to rearrange this to get an electric field strength. It's going to be Q over 2 pi epsilon naught LR. And by the way, just as a little informational aside, when you're writing equations in physics, there is, believe it or not, a standard order that people write this in. A lot of physicists themselves can't articulate it, but they always follow it. And this denominator is a perfect example. So within each numerator and within each denominator, people always follow the format first of numbers, so this 2, named numbers like pi or E or something like that, physical constants, epsilon naught, parameters, things that you could possibly change between experiments, so the length of the conductor, and then variables, things that you could conceivably change within the experiment, the radius. We could imagine moving a sensor from, we could imagine changing how far away the sensor is, say, from the center of the inner conductor. So that's the standard order: numbers, named numbers, constants, parameters, variables. But anyway, the reason we need this expression for the electric field is now we're going to have to work a little harder at getting our expression for the electric potential between these two surfaces here. There is an electric field, and since there's an electric field, there's a potential. But the thing is, here, the electric field is constantly changing. So this means we can't just say that it's E times D and call it a day. We are actually going to have to integrate this out. So since this is the lower voltage here on the outside, since this is the negative plate and the field lines are heading toward it, I am going to want to integrate going in from the outer surface to the inner surface. So my dr for my integration path, so let's make my integration path say this, like so. Some chunk of this integration path right here, dr, is going to point inbound. So with that, we can then say that the voltage is the integral from my outer plate to my inner plate, so from B to A of E dot dr. But now, since R is pointing inward and E is pointing outward, this is going to be minus E dr. So this will be the minus the integral from B to A dr, and then I substitute in my electric field, Q over 2 pi epsilon naught L R. Okay, if I want to be a little cute about it here, I can go ahead and pull out my constants, and I'll just flip the order of integration to make the minus sign go away. So then this will be Q over 2 pi epsilon naught L integral A to B dr over R. And if you look that one up, that's the natural log. So this will be Q over 2 pi epsilon naught L times the natural log of R evaluated from A to B. So this bit right here will be the natural log of B minus the natural log of A. And then if we remember our identities, that's the same difference as the natural log of B over A. So we can make it kind of as clean as we can by saying that delta V is Q over 2 pi, pi epsilon naught L times the natural log of B over A. Now what we want, we got V equals Q times stuff. We want to get it into prototype form of Q equals stuff times delta V, and then that stuff will be the capacitance. So we're just going to rearrange. So Q will equal, so then I have to multiply both sides through by 2 pi epsilon naught L. I have to divide both sides through by the natural log of B over A. And I have a delta V here. And then the stuff in front of the delta V I identify as being the capacitance. So I get that the capacitance is 2 pi epsilon naught L over the natural log of B over A. So let's take a look at what this is telling us, because remember, anytime you get an equation, this is a statement about nature. So remember, the capacitance tells us how good of a job this device can do holding charge. Well, if we make it longer, it will hold more charge. Makes sense. That increases the area of both conductors. What do I do with this log of B over A business? Well, we remember with parallel plate capacitors, we said that the closer the distance was between the two plates, the stronger the electric field, the more charge you could hold. And here we look at this and say, well, if these are closer, then B over A will get closer and closer to 1 the closer the plates get to each other. Well, the natural log of 1 is 0. So as B approaches A, this denominator approaches 0 and the capacitance approaches infinity. So again, it's the same deal. The closer you can space the inner and the outer conductors, the greater the capacitance will be. Alrighty. So I think you can probably guess where we're going next with this, and you would be right. It would be a spherical capacitor. Now you might ask yourself, where could you ever conceivably have one of these in nature? And I would submit to you, how about the Earth itself? The Earth is kind of spherical-ish. It's a little fatter around the middle, but hey, if you're as old as the Earth, that's probably going to be the case, right? Okay, bad joke. But you can say that the ionosphere is one plate, the Earth itself is the other plate. Could be useful for modeling things like lightning strikes, stuff like that. So in any event, it's going to be the same deal here. We'll say that we hold a charge plus Q on the inner plate, and we'll say that it has radius A. And we'll hold a charge minus Q on the outer plate, and we'll say it has radius B. Now the difference is both of these are spheres. You might want to try to follow what I just did for the cylindrical capacitor and do it with the spherical capacitor. The relevant integral is actually maybe even a tad easier. So maybe pause the video, give it a try, and then I'll debrief you on the answer. Okay, so we'll follow the exact same procedure we did before. We'll note that the electric field everywhere runs out symmetrically. And again, we can say maybe we forgot about the shell theorem. And so let's just go ahead and use Gauss's law to remind ourselves what the electric field strength would be. So we'll make a Gaussian sphere here. And here again, dA is always outward. There's only one surface. So E dot dA is just going to be E dA. So we'll take that. So starting with Gauss's law, we'll say integral E dot dA is equal to Q in over epsilon naught. And this is just going to be E times dA. We'll pull the E out of the integral. We'll integrate dA and be left with E times A. And then we know the charge inside is Q, big Q over epsilon naught. And the surface area of a sphere is 4 pi r squared. So we discover, to hopefully very little surprise, that the electric field strength is 1 over 4 pi epsilon naught Q over r squared, because the shell theorem does work here. All right, but if you ever forget what they are, you can always get them from Gauss's law, which is kind of nice. Next step, we'll go ahead and integrate E with respect to dr. So again, the outer conductor is going to be at the lower potential. So when we do our integral, we are going to want to make a path like this. And our dr is going to point like that. So E dot dr will be negative. So the voltage will again be the integral from B to A of E dotted with dr, which will be minus the integral B to A of E times dr. And then we can go ahead and substitute in our expression for E. So this will be minus, I'll just pull all the constants out right away. And while I'm at it, I'll drop the minus sign and flip the limits of integration. So I will have 1 over 4 pi epsilon naught Q integral dr over r squared from A to B. All right, so we go ahead and do that integral. It's minus 1 over r, right? So we get 1 over 4 pi epsilon naught Q times minus 1 over r, evaluated from A to B. Let's just flip the order of evaluation to make the minus sign go away. 1 over 4 pi epsilon naught q times 1 over r, evaluated from B to A. All right. So now we will do the substitution. This will be 1 over 4 pi epsilon naught q times 1 over A minus 1 over B. And generally speaking, it's going to be good practice kind of put this on a common denominator, so let's just do that. It's not strictly necessary, but it'll make the finished product look cleaner. Q times, putting this on a common denominator, we'll get B minus A over AB. Or I guess BA, if we want to be cutesy. There we go. So now we just need to rearrange this to get Q equals stuff times delta V to identify our capacitance. So Q equals, the stuff is going to be 4 pi epsilon naught times BA over B minus A delta V. And once again, we identify the stuff in front of the delta V as being the capacitance. So we get the capacitance is 4 pi epsilon naught BA over B minus A. So again, let's think about this. The bigger A and B are, the bigger the plates will be. So that makes sense in the numerator. That's just saying we'll have more area to hold charge. The closer A and B are to each other, though, the closer the smaller the separation between the plates, which again corresponds to being able to hold more charge, like in the other cases. Alrighty, so in the next video we will take a look at what happens if we have more than one capacitor in an electric circuit. Catch you over there.